Good, good. So again, I have to thank Signify for organizing this and for doing what they do regarding recruiting. So, but again, I believe I already said that. So just thanks again, and I'll proceed. So this is the motivation for why I'm switching to Scala3 now. So there's a lot of things that I have to do, and it's not much readable, like as instance of. So no, that's not a good idea. So that's why I'm trying to switch to Scala3, and I'm in the process, and I'll share my experience with it. So first, if you start converting your code to Scala3, by the way, there is a tool, but that tool, well, half works, half doesn't. So mostly you'll have to do it manually, like as of today. So main looks differently in Scala3. You can define any function, say that it's main, define types of the arguments, and they will be converted by the magic of Scala3, and then you'll handle it properly. Like this, we take a string and then maybe like more strings. That's optional. So that's compared to here where you had to do argument parsing. So that's one convenient thing. So another thing is you don't need curlies, right? So here the Scala2 code, curlies. In Scala3 you can write colon and then do like a couple of spaces maybe, or 4, or maybe a tab if you like tabs, and write your stuff there. So it's a little bit like Python or Haskell or whichever language you love. So classes, objects, traits, and also you can write end of your class or object or trait. So that reminds me Pascal, if you ever heard about this ancient language that I loved a while ago. So this is another nice feature. Also, implicits are written differently now. I'll get to implicits later, but basically, if you want to add an extension, like pimp my library, so you do it like this: an extension for an integer, and you define operation like this will add our x to the rational y. So you do that conversion and so on. Conversions can also be written using a new thing, conversion trait or class, whatever. So you define it. This is the shortcut of writing actually new conversion with apply method that takes an argument and produces a rational, for instance. That's how we did it in Scala2. This is, I wouldn't say it's longer, but it's more explicit. It's explains clearer what exactly do we do. More about extensions. So in Scala2, we wrote implicit case class shell and then did operations on that shell, like this and this and so on. Here in Scala3, we can write an extension with no boxing. So chmod on that string, and we do that. We define rm, remove this file, and we kind of save on memory, but it's probably these days not a big deal. We have unlimited supply of memory. Implicit with class type. So implicit on type T, we take a list and we produce last option. So it's the same as here in Scala2. At times, actually, the code that you write in Scala3, when it's desugared, it basically is translated into Scala2. I'll show you it later. Oh, this is wrong here because this catch should be moved 2 spaces to the right, and this too. So do while is gone. It doesn't exist anymore. But while it's there, and we don't need parentheses. So we specify our logical condition, and then we write do. So here we didn't have to write do. Yield for yield. Also no need for curlies or parentheses. Or you can write it like this. but you have to write do. If you don't write do, it will not compile. It will show you weird errors. So either do or yield are required. Try, also no need for curlies. This is like my mistake to have catch right in line with this. No, it should be moved. So Varargs. Varargs look just a little bit different, but less enigmatic. So remember, like when you had to learn, oh, you have to write colon underscore star if you want to pass a sequence to a method that takes a Vararg. Here in Scala3, you just write seq star, and that's the same as this one. Tail recursion. You know, if you write a tail rec for a method that is not actually tail recursive, you'll have a like error or a warning that will tell you, oh, it's not tail recursive. Here in Scala3, you don't have to say anything. The compiler guesses whether it's tail recursive or not and acts accordingly. So traits. Well, we have regular traits in Scala3, but the trait can also have parameters. So when it has parameters, it means it has a constructor. So you can have a class bird, extend this creature, and we pass 2 as the number of legs. And this creature has a constructor, so this constructor would be called before bird's constructor. It also means that you cannot have a trait that extends a trait with a constructor. So be careful, but you can use this word without parameters like this in this case. So we like give a hint again. Chicken extends bird, but also it extends creature. So you can write it like this, except that in this specific example is not very smart. So transparent trait. Remember in Scala2, if you have an object that extends kind, then another object that extends kind, and case object, right? Case object, it means it also implements product trait and implements serializable trait. And if you don't want to, and if you don't care about them being a product or serializable, so what do? Basically, we cannot do anything. We have a set of these. But in Scala3, we can say, oh, transparent trait S. And that transparent trait will tell object that when we push it somewhere, we will not need to pass all other traits that are implicitly included. Like here, we can have a set of kinds, and here we choose like either this or this, so the result is kind, and we don't say that it's product and serializable. So that's what transparent trait is used for. And we have enums. At last we have enums. So that's how we wrote it, like struggling all the time. How do you define an enumeration here in Scala2? You do like a lot of this magic, boilerplate, and eventually you get this. Or you can define an object with enumeration that has some values inside like this. So this is how we do it in Scala3. Enum direction, case east, west, north, south, as if there's no other direction. Or we can have directions with azimuth. So enum direction, and it takes a parameter, and we don't say like east has an argument, has a parameter, west has a parameter. It extends direction, and basically it's like this. So it's basically more readable. We don't produce anything new, but we just produce a more readable, a beautiful code. So having that direction, we can define turn right like here, a little bit different. Basically, it's like here, except that notice this double arrow right. They're not encouraged anymore, they're deprecated. So in Scala3, you'll have to write equal more. So we lost this beautiful character. Okay, that's life. So this is how things look like in Scala3. Also, we can parameterize enums, right? Here we didn't, here we do. So we have an enum eastward, well, and we define like good Eastwood, bad, and ugly. And ugly takes it's rowable. So, but we have three types, two types, like the type for good, type for bad, and we don't pass all these. This is how it's actually been like compiled, desugared before compiling. So that's what it is as a result. But you write it in a more like in a nicer way. So we can also have recursive ADTs. We defined an enum count with type parameter e, and define this when you take like a value of e2, which is what? Which is super type, right, of e. And then we produce a count of e2 by calling this constructor more. And more takes an e and takes a tail of e and basically produces this. So we can build something like a list, 3, 2, 1, and count done, because done is one of the values of count. So, and why do we do this? How does this colon work? It works like this. So it takes this O, which is of type int, and it produces a more, and so on. So we produce more and more. So the whole type of this is more of type e, and tail is count of e, meaning count of int. So it's all doable. It's an unusual enum. Basically, it's a generalized abstract data type. That's what we have just by using enum. So intersection types. Well, of course, we have, in a sense, we have intersection types. Like if we have class A and a couple of traits B and C, and we create an instance of instance X of type A with B with C, so it will be A with B with C. So it's like a product actually, but well, it's called intersection in GADT in Scala3. So in Scala3, it's denoted like this: A and B and C. So in a sense, it's just a notation, but probably it gives us more opportunities to do something. But that's how it looks like in Scala3. So, but union types are different. So suppose we have a trait fruit, and one fruit called plum, another apricot, and plum, which is like a mix of plum with apricot. So we have two traits. But can we produce something that is either plum or apricot or like plum? So let's try to define this like plum or apricot. It's either plum and apricot. It's left of plum because we pass it on the left, right? We can pass an apricot on the right. But how can we pass a plum? Is it left or right? It's hard to tell, right? But with union types, we can say, we can define the same fruit, plum, apricot, and plum. This is plum with apricot, so it's an intersection type. And we can define a value of type plum or apricot. And plum will also belong to this. Well, because it's not like either. We don't have to make a selection. We say, oh, it's a union. So plum is of type plum or apricot, and we can say just new plum, and it extends both plum and apricot. So intersection now belongs to a union, which is kind of natural, right? Another trick with union, we can like define something like this: error message, and define a message which is either int, as if we are in a language called C, or string, which means like we are probably like somewhere dealing with a JVM language. So if m is an integer, we do this, error number this, and we say app, so like we don't care about -1. Or if it's a string, we do this. So this makes like programming, I would say, more readable. Again, it's about readability, but also in this case, a union type that can have intersection. So that's what that. Yeah, that's union. That's push out in categorical language. So it's not something that you can easily have in Scala2. So nullability is not generally is not allowed, generally speaking. Like string is not nullable. So if you want to have something that can be a string or can be a null, you define it like this: a union type, string or null. And we can define this. We can check whether it's null by defining this extension method for something that is either T or null. And when we say define it and inline, meaning that it will be just injected in your code. It's like an annotation in line. Can be null, and we compare it with null because it can be null because it's a union, right? Then we throw an NP, and then we do this like ugly thing of casting to T. So this is runtime test, type test. So, but we can do it. We can eliminate nulls from most of our code by just using the word string. It's not null anymore. So now, how do we do implicits? Implicits are done pretty differently in Scala3. This is what we had in Scala2. I'm always trying to say Java. So we have an operation, we pass a patient, and a doctor is implicit. So if we know the doctor, that doctor will be involved. Like in our hospital, we have an implicit doctor, maybe like it's a small hospital, some doctor of this hospital, and then we do their job by applying this operation to each patient. And the doctor is known. So that's what we wrote here. Well, maybe like usually we pass not a doctor, but execution context if you are dealing with Spark or whatever. So in Scala3, we use different words. We say using doctor, meaning that doctor is being used here. So how this operation is being done, I don't know, but an alternative way of writing this, of defining this operation is this: take a person, and then take a doctor, but we write this question mark, meaning it's implicitly being passed. So it's using. So we can write op on person, and if the doctor is supplied, like we want it to supply doctor right here. So in our class hospital, instead of implicit lazy doctor, okay, lazy val, not lazy doctor, we say given lazy val doctor. And then we do that day job. We can write patient for each op, and that given doctor will be passed everywhere. Or we could write instead implicitly providing the doctor, like we say for each apply op to patient, and we use this doctor. More details are here. That's the documentation on GADT, context functions. So let's see what we can do more with doctor. There is a Q&A, but yeah, I don't think while sharing I can see the questions. So maybe like I'll get to the questions in the end. Okay. So say in Scala2, we had this object village with implicit doctor, like provided by something, and we import that doctor in our hospital from the village. So this village doctor will be doing all the surgery. Here, it's basically the same, right? In object village, we say given doctor and that doctor, and we import that doctor, and we don't need to write any given because we imported that doctor. Let me see. So let me take a look at this Q&A. Now, I'm sharing the screen, and it doesn't show me the Q&A.
Are you looking for the Q&A, Vlad? Sorry.
Yeah, I cannot see it. Yeah.
I can put the chat in there. I'll put the question in the chat for you.
Ah, okay, good, good. Mm-hmm.
There you go.
Yeah, I see. Well, that's a good question, whether I can match JVM Scala types. No, I didn't try it. Well, int and double, but basically in Scala2, right? You don't usually use like plain JVM Scala types. You write int with capital and double with capital. So in Java, that's the magic. Whether it will work for union types and matches, I don't know. I didn't try. So, but you can always launch REPL and see. So yeah, it's a good question. Oh, I see chat now. Okay. So where we were here, right? We can also pass implicits using given and pass them as a parameter deeper into the code. So here's an example. We want to sort a list. We want to sort it using insert method. So suppose we declare a type ord with less or equal method that returns a boolean, right? And we do sort, and we use this ord. And we pass this ord, what? We do insert. Insert also take this, so we pass it here, and in this ord, we use this less than or equal to, and we compare that. That's how insert sort works. So, and for integers, we define this given int ord just by comparing. So when we sort, now, when we imported this object ord, we can sort integers right away. Actually, we don't even, like here, we give a name to ord, like here, but we don't use this ord here. This insert will be receiving it because it also has this using ord. For that, we can have anonymous implicits. So this sort, like compare with this one, we say using ord, but we don't give it a name. But because we have this ord and this guy insert takes an ord, so it will be receiving this ord, and now here it doesn't need a name because it does this comparison. So that's one small little trick of passing implicits without giving them names and without basically like filling the namespace with the names we don't need. We can also do another thing. We can summon. Suppose we want to build a set of something, set of T, which depends on whether it's orderable or not. So if we have ordering for T, we build a tree set because it's efficient, right? It's efficient to have tree set if we have some kind of order or partial order on type T. If type T is small, like for instance, maybe byte or boolean, whatever. So if we provide this trait for T or type class, then we return a bit set. Otherwise, we produce a regular hash set. So we import so-called summon from. Compiler provides us, well, because when we compile, we know the type T. If we don't know, then we use this. But if we know the type T, we summon ordering for string, and we know that string is being ordered. So when we build a set for strings, we'll have a tree set. So we can do this like summon ordering string, and then println set for, and then get class. And it compiles properly, and the class would be not like something weird, but it's just Scala collection and immutable tree set. So compiler does like a lot of job for us that we didn't expect usually in like JVM-based languages, at least in Scala2. So dependent types. Dependent types is an area that is like being actively developed in Scala3. So So in Scala 3.0, we have some different dependent types. We'll have more in Scala 2.1, but the full like realm of dependent types will be only available in Scala 3.2. So here's what we have right now. One, when we declare one of type 1 equals number 1, now this number 1 is a number, and this one is actually a type. So as a result, in REPL, we will see 1 of type 1 equals to number 1. So we can like throw in some value x of type int and assign 1 to it. So it will be number 1 like of regular type int. And here this is dependent type that is only known to compiler. So we can define type value 2 of type 2 and try to assign 1 to it. No way, because number 1 is of type 1 and it's not of type 2. So we have a bad value for type 2. And these are like the document Scala 3 dependent types, which discuss all these in detail. But in short, we can have dependent types. So I remember like I had a dream. Can I define a vector that is defined? Can I declare a vector that is defined on exactly like numbers from 0 to 9? So a vector of length 10. Yes, you can do it now in Scala 3. Well, kind of, mostly because you know type erasure. So because of this, because we can have like dependent type, path dependent types, what we did if we wanted to have like a getter for a given type key, where value depends on the key, right? So we wrote like this. In Scala 3, we can define the trait key with type value trait key, which knows what the type of the value for this specific key, for each specific instance of type key. And so we can type db that takes a key, takes a value k of type key, and returns an option of this value. So again, it's implementable in Scala 2, but it's pretty clearly written in Scala 3. So combining all this together, like with given and extension methods, we can do like tricky things. Suppose we have a trait that is called like two's complement. So it's a representation of numbers where we know that abs doesn't exist for every given number, and negation also doesn't actually need for any given value. Like minus max value, what's that? Integer max value is integer max value. So we redefine abs and negation as optional, as function that return an option. So, and let's define this object two's complement that had this, and we produce two's complement of byte, where abs option for a byte is if it's a mean value. So there's no absolute, otherwise it's an option of regular option of abs value as defined in basically JVM. The same with negation. If we are negation of minimum, yeah, so it won't be maximum. So if it's a mean value, then there's no negation is not defined in it. Otherwise, it's an option of minus n y option because it's an optional type. So the same for short, right? We compare short mean value, and either we have the result or not. The same with and negation. Either we have a negation for a short or not. So now we define this, and now we have this like two's complements for bytes and for short that produces the correct value for absolute value or negation. So we could do this, or suppose we had two's complement like defined for a specific type, and we could write object two's complement. Well, you'll have to like import something, and we define an extension instead of this like given. We can define an extension for a given type n, and it's using this TC, and we define ups option and neg option for our n type given that TC. And again, like we can use these two complements for byte and short, and they'll find something. So here we combine extension and given and implicits. Now with that trick, we can also remember what we did with sort by insertion sort. So we can redefine insertion sort like this. We have given an ord. In that trait ord, we define extension methods for less or equal, bigger or equal through this LT method. For instance, for strings, we define LT as string compared to other string, and if less or equal 0, now this less is not the one that is defined in this extension because we are talking about integers. So string compared to string is either -1 or 0 or +1. So we do this, we have this LT. The rest is given by this extension. So because it's given by this extension, we only specify, we use this sort, and this extension in that trait gives us the opportunity to do this comparison. Like if XS is empty, okay, but if X is less or equal XS head, so we call this method. Where does this method come from? It comes from the trait ord where it's defined. So this combination, we like stuff it somewhere like in our common trait, and then we'll be doing these things. For strings, for whatever type we have, like persons, organizations, we can define this. And again, like the problem could be the same with implicit, right? Like when you hide your implicit somewhere, how do you know which exactly where it's defined and so on? So there's like a plus and minus in these operations, but it's doable if you're like if your code is well delineated and compact. So opaque types, that's another small thing that we have. So remember how we did it in Scala2. Suddenly we decided, let's not add meters with pounds and with ounces and whatever. So we defined class meter and define methods in it, like plus meter plus another meter. So we just take these values and create an instance, a new instance of meter. Or method centimeter, multiply a meter by 100. Oh, I forgot, I'm talking to Britain, so you know more about meters than we here in the United States. So in Scala3, you can write it in a more elegant way. Opaque types, you don't even define a class. You don't instantiate anything. You say that a meter is just a double, but in our code, we'll have those types meter and square meter. And we'll define a method that like produces a meter by method apply. So we can say like meter and then pass a double. And we add a couple of methods like plus. So we take a meter and add another meter. The result would be this, like meter of x plus y. So it looks like this, right? We write that it's a meter given a sum of two values. Well, actually, it's not, because it's just an opaque type. It doesn't take any space and doesn't instantiate anything. Basically, it's way faster. Compiler produces your code for you. So, and meter multiplied by meter, yeah, it's legal actually, this multiplication character. So we just multiply the values. But the values now will produce not a meter, but a square meter. But we can also multiply a meter by a double. So when we say m, we can say like 2.0 space m. That would be 2 meters. And we can multiply like 2 multiplied by like 2 by 6 meters. We'll have 12 meters, and that's how it is. So it's a multiplication of this meter by number a, and it's a meter. So here's a couple of examples. So we multiply 2 by meter, and we can, if we want to double, so it will be a double. Otherwise, it's a meter. And an area of square meters, we multiply 2 meters by 3 meters. So we'll have like 6 square meters. There is a problem with not using plural for more than 1 meter. And depending on the language, like 21 meter is also singular in Russian. So it depends on the language. The hardest is Latvian, I believe, is plural. So, but anyway, we can write this. And it can like used carefully, it can maybe let us avoid those problems with one Mars spaceship that just fell because people mixed meters with feet. You can also write code that works in compile time. Here's an example. We write inline def error with the message, and it returns nothing because it's an error, right? So it will throw in, it will produce an error. And we can define an inline failure with some operation, and we fail on that operation, and we write this code. So failed on whatever this operation, right? And if in our code we have this fail identity foo, it will, even identity, right? It will fail during compilation, and it will say failed on identity foo. So on which occasion you want to write the code that fails during compilation? I would not say no. I will try to use it, but it's nice that you can produce not only a compile time error, but a compile time error that has like details about what happened. Maybe when you generate the code, right? So it makes sense to have a compile time error that explains where we made a mistake, where our generator made a mistake. So another compile time trick is when we can guess a result type. Imagine we have class A and class B, extending class A, and class B has a method M. And we define this transparent inline def choose given a boolean, right? So it returns an A, an instance of A. A doesn't have a method M. And we do it like this. If B, then new A, otherwise new B. And you can write object one, choose true. And because it's transparent inline and we pass through, so it's a constant, the compiler will produce exactly new A. True, choose new A. And here, choose false. And the compiler knows it's false and it's transparent inline. So we'll replace B with true and find, oh, okay, no, not here, just new B. So object two will be new B and it will be known at compile time. So we can call M on object two. So basically it's good to have something that doesn't, that will be detected if there is an error, that error will be detected during compilation. Well, if we call like object one dot M, it just will not compile. So that's another nice trick where you can like get involved with compilation more than we actually ever did before. Maybe in schema, but I don't know schema. So summary, what's in and out? Private this, protected this. Why is it? I don't know, but okay. Private this is not there anymore. Well, it says it's out, but actually I use it like in a lot of my Scala3 code. So maybe it will be out eventually. So we don't try this, we cannot write this, the code this style anymore, where instead of using f of x colon unit equals, we write like this, procedure, how they call it, procedure, right? Also, we cannot have symbols. Symbols are gone in Scala3, so you cannot write it like this. This is a Unicode character, so no, it's not allowed. We cannot use like local returns. So, you know, in Scala2, you could write this weird thing, and basically, what does return do? This return do? It returns from the enclosing function. I don't know. I never tried, and I don't see why we should do. But it's available in Scala2 and not available in Scala3. Do while, as I showed before, we don't have do while, and you cannot assign a null to string. So this is good. So Java programmers will have, when they switch to Scala, they will have more frustration because they love nulls. And what you saw in these slides, export clauses, so you can export stuff. Like I didn't talk about export. Open classes in Scala 3.1, type lambdas in 3.2, unfortunately, because everybody loves type lambda, but hates to write them. We need them, but we hate to write them. Kind polymorphism. Well, it's like it's work in progress, but it's available. And what we can have is explicit null. So nulls are available, but you have to be aware. It's like is nullable annotation in, I don't know what, in Java. Yeah. So that's it from me. So thank you. And here's the book. This book is work in progress. Like this is the 5th edition of programming in Scala, 5th edition. So it doesn't currently, the current version that you can download as a PDF doesn't have like many features that are already available. So compare it with what they have in this reference. I didn't read Dean Wampler's book, so I don't know what's inside, but it's now, well, Scala3 is final. Is the book final? I don't know. I'll have to buy this book. So, well, he says like it's 1 minute read. Probably it's not the book. It's about like the announcement of the book. So thank you. So there are questions now.